descended on the town. So, all right, so before we get back to the notes, let me go through a couple of schedule changes. So the remaining info in Chapter 7 really needs today, which means I'm going to bump everything down by a week. And I will reopen the pre-Chapter 9 quiz, because now pre-Chapter 9 will be Wednesday. So I'll reopen that, gives anybody that is still on spring break brain, like me, chance to get that done if you forgot. So we'll do Chapter 9 on the 24th and 26th. The review will move to the 29th, and Exam 3 will move to the 31st of March. Okay? And then I will try to make up some time before the next exam, if possible. We'll see how that goes. Okay. What else did I want to say? Yes, all right, so I've gone through Chapter 9, and I'm not quite sure how to approach the information in that chapter. So I want you guys to take a look at it tomorrow maybe, or later today. If you haven't done your pre-chapter quiz, then take a look at it while you're doing that. There's a lot of chemistry type information in that chapter. And whilst we cover, the Krebs cycle and the energy systems, and those are kind of chemically and not immediately applied, I'm not sure the level of chemistry in Chapter 9 concerns me a little bit. But at the same time, we can't jump to the very applied and interesting information without understanding some of that other information. So I'm kind of in two minds how to tackle it. There are some very, very good talk to the expert boxes. There's some great student question boxes. So the kind of outline, all the box information and things is very, very good. It's just the detail of the actual text is a bit concerning. So I would like you to take a look at that. What I'm thinking is that I might skim that information as briefly as I can and give us enough info to cover for the application of it, like what happens in the acute situation, what happens in the training chronic adaptation situation. As long as we've got enough info for that to make sense, I think we'll be okay. But any feedback from you guys would be much appreciated, because it's a bit tricky to decide to tease out what to give you and what not to give you there. Okay, what was the other thing? I started sending back physical activity portfolio midterm version yesterday with feedback. I'm hoping I can get that finished this afternoon, although there's a lot of you in this class this semester, so I'll do my best. If I don't have too many questions during office hours, I should be able to make a good dent in it at least. So those will be back. There's lots of feedback there. Make sure that you read that and come talk to me if you need some more explanation, or if what I've said, then you're not sure how to move forwards, all right? Make sure that you check in with me. Okay, after all that, let's see. Where we got to here? All right. Okay, so we had covered our oxyhemoglobin curve. That's good. Gas transport. All right. Okay. So this diagram is a bit horrific. I'm going to make it a lot more simple. Okay? So just before I do that, I want you to remember that we're not just talking about getting oxygen from the lungs down to the muscle tissue. We're also talking about getting the byproduct of aerobic metabolism, carbon dioxide, out of the muscle tissue back to the lungs so that we can breathe it out. Okay? And if you can drag your memory back to before spring break, we had mentioned the fact that oxygen is predominantly transported on hemoglobin. Very little of it is dissolved into the plasma, the watery substance of the blood. Almost all of it is carried on the hemoglobin. When we look at removing carbon dioxide, it has 3 mechanisms of transport in the bloodstream. Some of it is dissolved in the plasma, up to possibly 10%. So again, not very much. A little bit of it is carried on the hemoglobin, but it sits on a different part of the hemoglobin molecule to the oxygen, so it's not in competition with oxygen to be on the hemoglobin. And then the majority of it is transported as bicarbonate. So when carbon dioxide is reduced to bicarbonate, that releases hydrogen. So we've got a little bit of acid issue there. Right? So this monstrosity of a diagram, I don't know about you, but that just overwhelms me completely. So we're going to make it considerably easier. Okay, so the blue is going to be the membrane of the lung, and the orange is going to be the membrane of the muscle and the capillary. Okay, and then remember our high-low law, all right? Because it plays a big role when we're looking at this picture. All right, so let's do oxygen first of all. Let's make oxygen black, make it easy. Okay. O2. All right, so our O2 is going to leave the lung and jump onto the hemoglobin on the red blood cell, right? Remember that much? So remember that if I'm moving across a membrane, then I'm going to see the gas molecules move from an area of high concentration to an area of lower concentration. Okay, so at this point, O2 is high in concentration, and over in the bloodstream, it's low, because remember, this blood is coming from the right ventricle, and it's at the point where it's had its oxygen used by the body, right? And so this blood is coming back to the lungs to get repopulated with oxygen to go back to the left side of the heart and out to the organs. Okay? So it's moving from high to low at this point. Now, here, when I'm leaving the bloodstream and I'm moving into the muscle tissue, ooh, what is that supposed to be? Okay, ignore the little squiggle. Right? Here, the law doesn't change. Okay? So in this instance, the oxygen is higher in the capillary and lower in the muscle tissue. All right? So you have to remember that oxygen in the bloodstream isn't either low or high. It's relative to the membrane that it's crossing. It's always relative to the membrane. Right? So for oxygen to move out of the bloodstream into the muscle tissue, there has to be less oxygen in the muscle tissue than there is in the bloodstream, in the capillary. Does that make sense? Or let me put it this way. Does it not make sense to anybody and you'd like me to do that again?
I thought that explanation was good.
Thanks, Kayla. Okay, all right, so much more simple than the diagram on the board. Again, not that that diagram, or sorry, the diagram in the book. The diagram in the book is much, much more detailed, but I don't think that given the kinds of jobs that we do, that we need to know it in that level of detail. All that chemistry, I don't think is helpful for us. Again, feedback. If you think I'm wrong and that I should cover more of the chemistry, please let me know. All right, so this time we're going to look at carbon dioxide. Okay, so we have carbon dioxide that we're making in the muscle tissue. that we want to get rid of to the bloodstream because we can't use it. It's a waste product. We have to just get it to a point where we can get it out of the body. Okay? So here, carbon dioxide is high in the muscle tissue because it's being made by Krebs cycle, and low in the bloodstream. Right? It gets to the bloodstream and the majority of it is going to dissociate into bicarbonate. When it gets back to the lungs, it rebuilds itself back to carbon dioxide. So I'm just going to leave it as carbon dioxide. Okay? So at this point, we have higher levels of carbon dioxide in the bloodstream than we do in the lungs. So we're high here, and we're low here, and that makes it easy for the carbon dioxide to move out of the bloodstream into the lung tissue, and then we breathe it out. Right? So remember that old story you got at school about we need plants and trees because they breathe in oxygen, they breathe in carbon dioxide and breathe out oxygen. And we breathe in oxygen and breathe out carbon dioxide. So there's this very symbiotic relationship between plants and trees and humans. Right? Again, it's not that carbon dioxide is either high or low in the bloodstream. It's high or low relative to the membrane that it's crossing and what's happening the other side of the membrane. Okay? Hopefully that is easier to follow than what we're going back to now. Okay. All right, so this is just putting it into verbiage, all right? The gas exchange at the muscle tissue, oxygen into the muscle, carbon dioxide out of the muscle, is due to the partial pressure differences, so the pressure gradient across the membranes. And you can see that down here on this diagram. All right, the arterial blood coming into the muscle has partial pressure of oxygen at around 100 millimeters of mercury. In the muscle at sea level, so this diagram is at sea level, it's about 40, so we've got quite a steep gradient there of 60 millimeters of mercury. Now, let's go back to our oxygen picture, right? Once we've got the oxygen into the muscle tissue, we still haven't got the end of the picture, okay? Because we said at the beginning of the semester when we were looking at the energy systems that we need the oxygen to pick up the hydrogens at the end of the electron transport chain. so that the muscle tissue isn't turning acidic, right? So I've got the oxygen across the membrane of the muscle, but energy system number 3, oxidative phosphorylation, doesn't occur in the sarcoplasm like energy system 1 and 2, right? Energy system number 3 occurs in the mitochondria, which are floating around in the muscle cell. So now I have to get the oxygen from the boundary, right, from the membrane to the mitochondria where it can do its job. And we have another transport molecule, very similar to hemoglobin, although it only has one ion, so it can only pick up one piece of oxygen at a time, called myoglobin. So anything with heme at the front is to do with the blood. Anything with myo at the front is to do with the muscle. Right? So it's very similar. You find it in skeletal muscles that we talked about. It's also in the cardiac muscle, which isn't surprising because remember, cardiac muscle is very similar to a type 1 or works in a very similar way to a type 1 fiber from an energy standpoint. Right? So it picks up the oxygen. We don't need to worry about it reversibly binding. Not even sure I could explain. If I studied it, I would have a hard time explaining it. It picks up the oxygen. It assists moving the oxygen across the cell, dumping it at the mitochondria. Okay? So there's never a point where there's no oxygen in the muscle cell because this molecule, this myoglobin, is kind of floating around and it mostly has an oxygen attached to it. If I'm working anaerobically, that oxygen stays where it is on the myoglobin. But, as we said, we're very rarely working totally anaerobically. There's always a little chug, 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 chug aerobic bit going on. And we use that oxygen from the myoglobin. All right? Or at that 2.5 minute, 3 minute crossover point between glycolysis and system 3, oxidative phosphorylation. Okay? Then we've already got a little bit of oxygen in the cell ready to go. Right? When we're working aerobically very hard, then that myoglobin is dumping off oxygen all the time. One of the reasons we have that epoch, remember that extra breathing that we do at the end of any physical activity? One of the factors, if you go back and have a look at the diagram that had all the factors in a circle, one of them is the fact that we have to replace the oxygen we stole from the myoglobin so that it's got its oxygen sitting in the cell again. Okay? Now, given what the myoglobin is doing, which type of muscle fiber has the highest levels of myoglobin, do you think? Skeletal muscle fiber. Transporting oxygen, which type of muscle fiber uses oxygen best? Which type of muscle fiber does an endurance runner have more of than a sprinter?
Type 1, right?
Yay! Well done. Excellent. Yeah, type 1. Right? Our type 1 fibers are very, very good at resisting fatigue because they use energy system number 3, Krebs cycle and electron transport, predominantly to make their ATP. Right? So if they're going to use a lot of oxygen to make their ATP, it stands to reason that they have more myoglobin available. Right? Type 2A, the one that's kind of in the middle, it can do a bit of both, has less myoglobin than type 1, but more myoglobin than a type 2X, which is the really powerful, fast one that doesn't do very well at using oxygen at all. So it wouldn't need much myoglobin. Okay? All right, so breathing's an interesting mechanism because mostly we breathe involuntarily, right? We don't really think much about breathing. But we do have the capacity to take voluntary control of our breathing and hold our breath if we want to, right? We're going to jump in the swimming pool. So we have several different factors that play a role in the control of ventilation. So we have a respiratory center here in the medulla, right, which is inside the pons in kind of the brain stem, right? And it can serve as a pacemaker and generates this kind of rhythmical breathing pattern that we have if we're asleep, unless we have sleep apnea, or when we're just sitting watching a film, right, or reading a book. And then how fast we're breathing and how deep we're breathing can be controlled by higher centers. There's also lots of chemoreceptors all around the body. So there's chemoreceptors in the medulla, but also in the respiratory muscles. There's chemoreceptors in the aortic arch, right? So they're all very sensitive to the levels of pH, the acidity, right? So when there's more carbon dioxide being carried around, there's more hydrogens available. Remember we said the bicarbonate drops, carbon dioxide drops a hydrogen to become bicarbonate. So they're very sensitive to that. Okay? We also have stretch receptors in the respiratory muscles that can send information to the central nervous system. Okay? So there's all this information that's controlling this involuntary breathing action that we do. Right? Now, there's a technique that swimmers use, and I've heard sprinters possibly use it as well, about using hyperventilation. Right? So, if you watch really advanced swimmers, so this is not something you would do with your beginner aqua aerobics class or your beginner swimming class, right? This is a very sophisticated technique. So when you watch them and they're standing ready to dive in, you'll often see them going, right? And many people, myself myself included years ago before I learned the truth, right? Imagine that they're breathing like that to get more oxygen in their lungs and in their bloodstream, because they're going to dive underwater, and the human body is much more aerodynamic underwater than it is once it hits the surface, and it's got the surface tension of the water slowing it down as well. So they want to stay under the water as long as possible when they dive in, right? And so we think, oh, they're breathing in more oxygen, right? Now they're not. What they're doing is blowing off carbon dioxide, okay? Because it tricks these chemoreceptors into thinking that there's enough oxygen available and therefore I don't need to breathe. Right. So let me go back to our whiteboard. Oh, I can't wait for you guys to be actually here in person. This is so frustrating. All right. So, what we have when we're at rest, right, is generally in a relative situation, because I can't do an arrow here. So we've got high O2 relative to low CO2 and low hydrogen. Right? So when we're at rest and we're not doing very much work, in our bloodstream there's relatively high amounts of oxygen because we're not using it, right? And there's relatively low amounts of carbon dioxide because our muscles aren't working. They're working aerobically at rest, but they're not working very hard. So they're not producing a lot of carbon dioxide. Okay. In exercise, what happens is we get a relative low oxygen, high carbon dioxide, and high hydrogen. Oops, hog hydrogen? Who knew? High. Okay, so in this situation then, our pulmonary ventilation, our breathing rate, is low, right? So we've got low pulmonary ventilation. And in this situation, we have high pulmonary ventilation because the chemoreceptors are recognizing that there's a high level of carbon dioxide available, and they want to get rid of that carbon dioxide as quickly as possible. Okay? So when we hyperventilate, we're not breathing in oxygen, we're blowing off carbon dioxide to trick the brain into thinking it's in a resting situation and it doesn't need to breathe very fast. So I can hold my breath for longer under the water. Now, I've heard that sprinters will sometimes use this technique as well, so that, you know, especially 100-meter sprinters, because if they can delay breathing for the first 50 or 60 meters, then that's energy they can use for running, and they don't have to waste time breathing. they've only got like 8 seconds to get down the runway, right? So questions? It's really an interesting mechanism. You know, we trick our brain into thinking it doesn't need to breathe deeply. So we don't see very much adaptation in this system compared to our cardiovascular system and our muscular system. We don't see that level of adaptation here. Okay? We do have 3 phases when we look at the difference between rest and going into exercise and exercising. We have these 3 phases of breathing, of pulmonary ventilation. Okay? So remember that respiratory muscles have a very high oxidative capacity, right? They work very much like type 1 fibers again, because they've got to keep working all the time, all the time, all the time, all the time, right? So they're relatively fatigue resistant, not quite as fatigue resistant as cardiac muscle, but they're relatively fatigue resistant, okay? So as intensity gets higher, we see some changes in the chemistry of the bloodstream. So let's look here, right? Here's my resting phase. And just like we saw with heart rate, typically, especially in an experienced person, you're going to see pulmonary ventilation go up just a little bit before the exercise starts, because the body's getting itself ready for the exercise session, right? Here's our start of exercise. So this is phase 1. We see a rapid change in pulmonary ventilation. And then we get phase 2, where we kind of peak out and we start, the increase in pulmonary ventilation is much slower. Phase 3 would be a steady state. So I'm chugging along and my pulmonary ventilation, my breathing is providing the oxygen I need to do the level of work that I'm doing. And then we stop exercising. But it takes quite a long time for our breathing to come back to rest. So remember, this is like our epoch phase. Okay? So phase 1 is prior to and at the start. We see an abrupt increase. Right? So part of that is anticipation, and then once the anticipation has kicked in, then the stretch receptors start to recognize that I'm breathing more deeply. Phase 2, quick rise to steady state. Phase 3, fine-tuning of that steady state. As long as we don't hit a hill, in which case it would go up again. If what we do is stop, then we've got our epoch, right? So typically, pulmonary ventilation can easily match the demand of submaximal level physical activity or exercise, right? We don't have any problems. So in most individuals, pulmonary ventilation isn't a limiting factor for performance, but in individuals who have asthma or individuals who have COPD, then pulmonary ventilation does become a limiting factor. But in a typical picture, right, then pulmonary ventilation doesn't change very much. Right? It does seem, though, that there's some training adaptations that occur. And this is where the new book has expanded this chapter quite a bit. Okay. So respiratory muscle training, RMT, initially, like many things that we see in exercise physiology, initially was a clinical treatment for people who had respiratory diseases, COPD, emphysema, things like that. And it's training your breathing in, okay? Mostly. Do a little bit of training on the expiration, but it's mostly the inspiration, because remember the expiration you don't use the muscles so much, they're more just relaxing, unless you're working at very high intensities, and then they tend to contract and push. Right? So the idea is that if we can strengthen the respiratory muscles, then that might improve performance, even though it doesn't change pulmonary function, right? So there's this connection between metabolism and ventilator function. And I'm going to look at the respiratory training. I'm not expecting people to look at the ventilatory threshold information, but remember that we did do ventilatory threshold estimates in lab, and we said that ventilatory threshold is a kind of guideline for lactate threshold. So if you're interested in that lactate threshold training paradigm, there's quite a bit more information at the end of the chapter here on how to use ventilatory threshold as a training device. Device? Yeah, that's not the right word, but you know what I mean. Okay? So the proposition then, the idea is that if, in the same way like we would condition our skeletal, our locomotor, our skeletal muscles, if we condition our breathing muscles and make them fitter, then we can maybe see an improvement in performance. One of the mechanisms that they think is playing a role here is what they call metaboreflex. So the metaboreflex occurs at around 85 to 90% of VO2 max. And what happens is the sympathetic nervous system stimulation of the respiratory muscles, when you're at that level of work, is basically plateaued. It's at its highest point. And so norepinephrine, which is one of the hormones that is being stimulated by the SNS, shifts from the respiratory muscles, because they can't do anymore, over to the skeletal muscle. And norepinephrine causes vasoconstriction in skeletal muscle. So that then leads to fatigue, because if I'm getting vasoconstriction, then I'm not getting as much blood flow to the muscles that are working very hard. That means I'm not getting the same amount of oxygen or the same amount of glucose that's coming from the liver. Right? So we see fatigue in those working muscle groups. So what they think might happen is that if we condition the inspiratory muscles and make them stronger, then that trigger point of when that reflex, that metaboreflex occurs, could be later on. So maybe it doesn't happen until 95 or 96% of VO2 max. Right? So in theory then, delaying the vasoconstriction at the muscle tissue would delay fatigue. at the muscle. Right? So it might improve the scenario at very high intense exercise levels. Nothing that you do, none of that training is going to change your VO2 max. None of that training is going to change lactate levels and lactate thresholds. Right? So RMT can be endurance work, or it can be resistance work. It's typically resistance work, right? And we'll see if I can go quickly enough in a minute. A training program. If you're doing endurance adaptations, then what they think happens, so the other mechanism to delay fatigue, is that you see a change in the recruitment of the inspiratory muscles. So instead of using the diaphragm primarily, the other muscles, so the intercostals, the sternocleidomastoid, I cannot say that word, and there's one other, can't remember. Those ancillary muscles take over, and that gives the diaphragm a bit of a rest, and that delays fatigue. And I would say, have a look, because this is really interesting. Go to page 208, and what they're saying is they think that this change in the trigger point for this reflex occurs in running and cycling, but probably doesn't occur in swimming because swimmers are already trying to expand their lungs against the pressure of the water that they're in. So they're already doing like resistance training just by swimming, I guess is the idea. So for the kind of resistance type ones, it works, it adapts in a similar way to skeletal muscles. So you've got to overload the muscles to see change, right? The recommendation for intensity is 50 to 70% over 1 RM of the inspiratory muscles, but I don't know how you would find that out. I didn't have time to look that up. Duration, 1 to 2 sets of 30 to 40 breaths, twice a day, 2 or 3 days of the week. Progress it as you see adaptation, so as you feel stronger, I guess. The recommendation is it's important to be in the same position as you would be in the event. So like for rowing, you wouldn't want to do these exercises standing up, I guess, is what they're trying to say there. Same for cycling, right? You'll see detraining and deconditioning. We haven't really talked about detraining much yet. But so if you stop the work, it doesn't stay. It's a muscle, right? If you stop stressing the muscle will lose the adaptation and go back to its primary situation, right? But there are maintenance programs that can be useful, and technique is important. You can read all this. I'm rushing because I'm late, and I do have one more thing I wanted to point out to you. The exercise equipment, and we'll come back to this when we look at altitude training. There's a lot of disagreement on particularly the face mask type idea, all right? And I've been very skeptical of the face masks for a long time. About 8 years or so, 9 years ago, a student specifically asked me about that, and I did some research. And the claims that the major company that makes these masks were making on their website were ludicrous, okay? Now, they have adjusted the website, I have to say. The last time I looked at it, it was much more reasonable. But the altitude masks don't really create altitude. What they do is make it harder to breathe. Right? There's a valve in there and you can close the valve down and make it much harder to breathe because the air's not coming through. They don't create a hypoxic environment. Okay? There's no way of cutting down the amount of oxygen in the air, at least not that I know of. I put a link here for you because this is a very interesting article. I also have found the article that the chapter discusses, the review article about all the equipment that can be used. So it's a 2018 article. And this is a brand new book, so I don't know if that means that there's nothing new since 2018. But I do have that article if people are interested. It's a research article, but it's a review of research, so it's a little bit easier to read. If you'd like that article, let me know, I can send it to you. Okay. So, ta-da! That is chapter 7. So on Wednesday, we will start chapter 9. As I said, if you get a chance to send me some feedback on the level of chemistry that is in that chapter, please do. Because I'm not quite sure where to pitch. As I said, it's a brand new chapter. I haven't taught it before, and I'm not quite sure where to pitch the information so that it's usable for you. Right? Okay. We're done. Have a great afternoon.